So when talking about data science, which is taking large amounts of data, collecting it together, reading through it, and trying to come up with some interpretation of what this data means, one popular component of it is the SQL, structured query language, where you read information directly out of a database. So a major part of data science is knowing SQL. So suppose, for example, we had an online store like Amazon.com, where you log in and you browse all the products we sell, and you grab some products and you put them in your cart, and then you grab some more products, put them in your cart. Eventually you go to checkout and you pay with your credit card or PayPal, and you hit purchase, and they eventually mail the stuff to you. So as people are putting stuff in their cart, and we know information about the person because they became a member of our website. So how old are they male, female, what stuff have they bought in the past? We know information about them, and we can make suggestions for products they might want to buy. And if they buy them, that's more money for us, I guess, right? So suppose we had a table called members, and the members had a member ID, a first name, a last name, a password, and then maybe some information about them. Are they male, female, what's their date of birth? Okay. They open up a cart, so we might have a cart ID, and then we might decide all carts are controlled by a member. So right now we're making the decision 2 members can't share a cart. Okay. Don't have to do that. Do you know any online sites that multiple people can share the same cart? Does that happen? Can 2 people who work at the same company share like a company cart? Okay. All right, so then we have products. These are going to be all the products that we sell. So we can have a product ID, the name of the product, the price of the product, and maybe a description of it. Obviously, we'd have more stuff like pictures of it and that kind of stuff, but just enough to get the point across. Now, if we have a cart which has a bunch of products in it, now a customer's taking a cart and putting products in the cart. Maybe a good name for that table would be cart products. It's a cart followed by a bunch of products. So we could, now, here's where we have a choice. We talked about this earlier when we originally learning table design. Should we say the cart, should we have a cart column and then maybe pick a finite number of products, like 10, and have 10 product IDs? And then each of the 10 products have a quantity and a price, and then that would limit us to say, oh, people can only buy 10 things, and then that cart is full. Or we can have the table say every time they put a new item in their cart, we add a new row. So that same cart has now a new product, and this is how many they want to what the price. So that's a design issue, and let's say we did it this way. Now, if a person put 4 items in their cart, they would generate 4 rows in this table. Every product that goes in a cart, there's a new row added. So product 1 goes in cart 1. Now product 2 goes into cart 1. Product 3 goes into cart 1. We keep adding rows. And then when you finally make a purchase, we would have purchases. This member bought everything in this cart on this date. Now we might actually want to keep other information like what was the total they paid, whether any discounts and that kind of thing. But this is just enough to get the point across of an online store. So suppose we now wanted to collect some data science data. It's very popular to have separate tables just collecting your data science, not what the people are buying and how many of them are buying, but information about their purchases. So for example, we could have products that are popular to certain age groups. Now we said that we had the customer's date of birth. So we know their date of birth. We would have to, from that, calculate their age based on when they were born and what is today's date. We would then calculate their age. And whatever age group they're in, they're going to keep, as time goes on, they're going to keep moving across age groups. So we have to calculate that every time purchases are made. So we could say things like select, we could run an SQL statement that says select the product IDs and how many of them are there. From the tables, this is now the table's products, cart products, purchases, and members. And then we have a big where condition where the product ID in the product matches the cart, well, the product that was in the cart. The cart product's cart ID matches the purchases cart ID. The purchases member matches the member. We want the person's, because we want to get to the member table to know what their age is or their date of birth. And then we say their date of birth is between some date and another date. And every time we run this, we're going to be changing this date to match how old the person is to a date based on today. So we have to remember that age is a dynamic field based on the date of birth plus today's date. So this query should take into account the date the product was purchased, not the date the query was made. So somebody whose date of birth makes them currently 30 years old purchased something when they were 29 a year ago, we should say this product was bought by a 29-year-old, not a 30-year-old. It should be whatever their age was when they bought it. So that's something you have to just make sure, however you're doing your data science on this product is bought by people in a certain age group. And products by the customer's gender. So we could do a query, we could have another table. Oh yeah, so one thing I wanted to say was, it might be popular if you're creating data science tables that are in your database, and maybe give it a name that reflects that, like maybe DST, data science table, and then underscore, what are we doing? And we're calculating these products are bought by this particular gender. Let's say that's something we're interested in doing. So we could say select the product ID and account from products, carts, purchases, the same intersection of our tables, and say where this product ID, well, the product we're looking at was in a cart. The cart was purchased by one of the carts that were actually purchased. So it's not someone putting something in their cart and deciding later to not buy it. And then finding the member who that is, and then saying is that member's gender female. So we'll count how many times was this product bought by a female, how many times was it bought by a male. And if they're about even, then it's really a gender neutral product. But if one gender buys it much more than the other, then when someone logs in, we might say this product may interest you based on who they are. So this is, yeah, so what we can do, as you realize, we can probably make an endless number of data science tables based on our little online store. Could have lots and lots of ways of predicting what customer would like which product. So there might be some interesting questions. We might want to say, would a female user between the age of 60 and 74, let's say a female user between the age of 60 and 74 is currently logged in. Should we suggest products that are very popular among people between 60 and 74, but not popular among females? Well, maybe this customer might not be interested in that. One of our data scientists says they might be interested in the product, the other one says they don't. Should one cancel out the other one? Should we suggest products that are very popular with females, but not popular with people in this age group? So is one of these categories outweighs the other, or is it just if one of them, if the count is low in one, we should ignore the high count in the other one? And what is the definition of very popular and not very popular? Is it like 5% of the, more than 5% of these people buy it, that means it's very popular? If less than 1% of that group buys it, that means it's unpopular? What's the definition of it? And this is now where statistics comes into play. How do we decide what is very popular and what's not very popular? So in data science, things that you can do, there are a lot of tasks we want to do in data science, and ones that you can do using SQL is data aggregation, taking data and counting up totals. So for example, doing counts, we know from our SQL statement. So we can add up counts of products bought by, alongside of other products. Products bought by customers who are in any kind of group we want to group them together in. Ranking, we could then take those counts and say this is the most popular product bought by a person in this group, or a person who's also bought this product. Here's the second most popular, etc. So we can rank them based on their counts. We could do bucketing of data. So for example, these age groups, 23 to 34, we could kind of make up our own age groups and try to just see which, rather than say 24-year-olds buy this and 25-year-olds buy this, we could group them together because 24-year-olds and 25-year-olds might buy the same types of products. So we can decide which are the most effective ways of grouping our data together. Then doing statistics on products, which are the most popular, products bought by one person, bought by another person, how far do people deviate from the norm, we could do that using SQL statistics. And then also windowing, which is products that are bought this week or bought by people just after they turn 21, so we could make windows on our customers and say, if you're inside this window, it's very likely you'll buy this product. Okay. So then if we wanted to have if we wanted to calculate something like people who bought this product have also bought other products, we can make a data science table called alsoBought, and we say this product, if someone buys this product, we could have a fixed number and say, we'll name the 4 most popular other products they buy in order. So let's say also, well, maybe also 1 product ID, also 2 product ID, also 3, also 4. So we could say select the product ID and the quantity from carts and products. So these are people who bought products where the cart number is in the set, and then we do another SQL statement. So this is a compound SQL statement. And we could say select cart IDs from carts products where this product, a particular product was bought. So we're looking at one particular product and we want all of the other products that were in the same cart that this one was bought. Right? So we're picking a particular product and we're saying, I want all the carts that that product was in, and then I want all the other products that were in the cart with that one, and then I want to count them up, how many times that happened. So what are some issues with doing this type of counting in SQL? So for example, suppose a product repeated for the same customer. Suppose customer A bought 2 of them, and then B bought 3 of them, A bought 3 of them, B bought 2 of them, A. So in other words, product A was bought 2 times, and then 3 times, and then 2 more times. That's really like product A was bought 7 times by the same customer. Just because this could be a customer who just keeps making a bunch of small little purchases, right? They put 2 things in the cart and they buy it, they come back the next day, 2 more things, and so on. Someone else might just make one big purchase at the end of the week, and then we want to know that the same customer keeps buying the same product, they just do it on the next day. And this query won't pick that up because this is based on carts. We might want to do another query based on a customer who's buying products over several carts. Okay. And then we could do, so here's another issue with saying I want to record for every product. I want a table that has for every product what are, I'm randomly picking a number of 4, the 4 most popular products bought along with that. So if I'm collecting data for a month and I have the 4 most popular products, now a new day goes by and a few more purchases are made. Do I want to go back over the whole month and redo this calculation, or should I just take today's sales and add it to these existing sales? Well, then what I need to do is record how many of each of these products were bought. So if, let's say, the one that's in the number 2 spot, more purchases come in on that, that should move to the number 1 spot. But because I made the decision to only keep the 4 most popular ones, there could have been a 5th most popular one that over last month was in the number 5 spot, but now it's becoming very popular and it's moving up through 1, 2, 3, and 4, but I never recorded it, so it'll never make its way to the top. So every once in a while, I may have to recalculate everything based on all the past data. Okay. So if a person buys products in 2 different carts, would this query catch it? And the answer is no. This is only catching what products were in the same cart as another product. So we might want to do another pass where we say pick all our picked our different customers, take all the carts they bought in, let's say all the carts in the last 2 or 3 days, and consider that one big purchase. Say this person buys these types of products. And then the other thing is a customer may be doing shopping for a group of people, like an office party or a Christmas party or something like that. So they're going in and buying one thing for you, and one thing for you, and one thing for you, and then we're saying, oh, people who like the thing you like also like the thing he likes. But that's not true. You're two different people. So they got into the same cart, and the data is actually confusing us. So we have to somehow statistically remove, every once in a while, 2 products that have nothing to do with each other end up in the same cart. And we want to make sure if that doesn't happen too often, we don't say those products belong together. Okay, then the other thing is if we decided that we'd like all of our data science data to be controlled by our database, every time purchases are made, might cause us to kick off some type of SQL statement that collects data science data. And we might want to use triggers and events, which we've talked about earlier in our course. So the idea is that we could put a trigger on the we could make a trigger called alsoBought, and every time somebody puts something into a cart, we do a select statement and we update our data science tables. So is there what would be the advantage and disadvantage to us saying within our SQL, so within our database, in other words, we don't want something outside our database updating our data science tables. What would be the advantage to doing this as opposed to letting it go outside the database? So here's what I mean by outside the database. Hopefully, we're now starting to realize that when we're doing data science and recording content into our tables about our products and who's purchasing them, whenever people make purchases, we want to then update our tables about the purchases. Should it be done by the database every time the database is touched, or should we have some programming language? And the popular programming languages now that do data science are Python and R. Those are programming languages where we can code up SQL statements. If somebody wants to buy something, they take a product, put it in a cart. We can then say, now that they've done this, I want to code up an SQL statement to update my data science and kick that off and make an update. If we do that, our database now is counting on whoever programmed the R program or the Python program to make the correct update. We haven't created a database that correctly updates itself. So if we create a database that triggers every time an event occurs, we go and have our database automatically update our data science tables, then we feel as database creators that the database is working correctly, instead of having a table and just hoping someone who's coding up in Python or R is doing the right thing. So there is the idea that we could have triggers set every time a move is made on our data, we have our data science tables automatically updated. And what's the advantage and disadvantage to doing that? So for example, if we had an SQL statement like this, so we're selecting all the products that are very similar to a product someone just put in their cart, and we return that back to them, that would mean every time somebody puts something in their cart, this event gets triggered. It might be a good idea to have a query like this done at 3 o'clock in the morning, because it's going to take up some time reading and writing from our table. It might be better to have it done at 3 o'clock in the morning. We just go get the results from a programming language like, Python or R can just go and read the field out of the database and send it to us. So there's a little bit of a debate. Should we make our database and our data science triggered so that the database manages everything? Or should we have it set up so that we're counting on the business intelligence of our products are being met in both the database and in our programming languages, like Python and R? So in other words, each one is counting on the other one to not make a mistake, as opposed to saying, I want the database to be perfect. The problem is when making the database perfect means the updates to our data science have to run every time someone makes a move, and we might not want to spend that time while customers are shopping. We'd like to do that at another time. So it might be best to have programs like R, Python, PHP, etc. determine on an as-needed basis what our business logic is and divide that up between the programming and the SQL. And that's kind of a design level of your application. Okay, so we want to be able to answer questions, and we can look at past data, who bought a certain product. But suppose, for example, somebody bought, any of you have a Fitbit? Well, you know what it is? What, like it counts up, I don't know what it is. It counts up how many calories you're burning? Something like that? Okay. So maybe people who buy this product also buy running shoes. Right? So is that what you call these, running shoes? Or sneakers? Sneakers? Oh, okay. I thought when I was a kid they were called sneakers, now they're called running shoes. But all right, so you call them sneakers. All right, good. So, so now, suppose somebody puts this in their cart. Well, if we had some statistical data that says people who buy this product also buy some other product, this product has different attributes about it. One is what color is it? So this is like teal, right? Greenish blue color. And people who buy this might be interested in fitness, and maybe we notice they buy running shoes or sneakers when they buy this product. But maybe the color of the product, the color that they put in, they might want to buy shoes that match. Maybe running shoes that match the color of this might be important to them. And we might not pick that up when we start saying who buys Fitbit. So now we have to say all the people who buy a teal colored Fitbit, what do they buy? As opposed to someone who buys a dark blue colored Fitbit, they might buy different products. And maybe a certain color is this, I don't know if this is a male or female color, and if so, maybe if you buy a pink Fitbit, maybe you're looking for female running shoes, and if you buy a blue Fitbit, maybe you're looking for male running shoes. Or maybe whoever you are, if you're logged in and we know what your gender is, then you're probably looking for running shoes that match your gender. But then there's also customers who we don't know who they are. Right? Do you ever shop online? What do they call that? You're shopping as a, you're not logged in. You're a guest, yeah. You log in as a guest, so nobody knows anything about you. So do you shop as a guest? That's kind of a side conversation. Do you like to shop as a guest or a logged-in member?
Logged in.
Yeah, well, a lot of people like being a guest. I don't know why. They have to keep logging in, and then when they make the purchase, they have to give all their information again, rather than open an account. But anyway, it is popular to log in as a guest. If you log in as a guest, we don't know what your age is, we don't know anything about you. So if you put this item in your cart, we don't know if you're male or female. We might suggest this to you and you're not a woman. I don't know. These are female. I think these are male shoes, these are female shoes. Okay. But we don't know who you are. But if we know who you are, then that might determine what we suggest. So the point, I mean, I'm just kind of closing out this conversation is that the idea, it's one thing to say we could come up with a bunch of SQL statements to do our data science, but depending on who you are when you're logged in and attributes about the product, like what color is it and what size is it and other things like that, are going to determine our products that people who bought, people like you who put this item in their cart, also like these other items, will have a lot of different things that are going to cause us to come up with different products. So it's not as simple as just for every product. It's not as simple as just saying for every product that there is, let's see how many times someone bought this product and put something else in that cart. There's other attributes about their cart and who the people were and how old the people were and all that stuff that determines whether we're going to suggest it to. And then another thing we can determine by, again, I'm using the example today of just purchases of products. So if we have a product that, let's say for a particular product, there are the most popular, the second most popular, third and fourth most popular product that are also bought with this one. Suppose, what would you think would happen if there's a particular product like a Fitbit, and it's popular to buy that with running shoes, and then maybe the next thing would be like, what else do people who run buy? Running pants, running shirts. So you might think that this product and this product get bought together a lot, right? Because this product is in the same cart with this one, and this product is in the same cart with this one, so you might think these two would be in common. But what if you found out nobody buys these two together? What would that say to you? I'll give you an example. Suppose, so these are Puma, that's a brand that makes sneakers, Puma shoes, and these are Adidas, the three stripes is Adidas. So suppose people who buy this product, a lot of times they buy Puma shoes with it, or they buy this product and they buy Adidas shoes with it, but they never buy this product and this product and this product, because they only need one pair of shoes. So what we might find is if this product is purchased a lot of times with this one, and this product is purchased a lot of times with this one, but then we do an analysis on these two products, and they're never bought together, these two products might be competing products with each other. That people would only buy one of these and never buy both of them. And from that we can say, oh, people who buy this product might also be interested in this one because they compete with each other. And that might be a new piece of data. We'd never find that looking through, but we would never say, we would never find that this product and this product are sold together, so we would never know to suggest it. But if we notice that these two products end up in the same cart with this third product, then we realize these could be a replacement for the other one. That's another thing we'd have to find. So just our basic SQL queries won't find simply what products could be offered as an alternative to another product. So some products could be, if you buy this, you may also want this. And another thing we could say, if you're interested in this, you might want to forget about this one and buy this one instead. And we have to go finding that stuff. So yeah, it's very popular now if you go to companies that have big data. So what's a company with big data? A company that has a lot of users, and the users are doing a lot of stuff, like uploading pictures and tweets and that kind of stuff. So if you go to Facebook, and at the bottom of the page, they have these links that nobody ever looks at. And one of the links is careers. And if you click on careers, and you type in, so this is Facebook as an example, if you type in data science, there's tons and tons of jobs at Facebook on data science. So I've been scrolling up and down, I've only gotten this far. Let's see, so you can't see it. So, so lots and lots of jobs on data science. And so let me see, try to pick an interesting one. Data scientist. Let's see. So, I don't know if this is going to come out, but so they want you to have an analytical degree in computer science, engineering, math, statistics, 5 years experience, heavy emphasis on data analysis, 3 years hands-on experience in interpreting data. So what does interpreting data mean? looking at data and going, what's the meaning of it? Well, if, this product was bought with these two other products, but these two other products are never bought simultaneously, those could be competing products. This is really open. I don't know if this, you can get a degree in that, but it's just open to interpretation. They want you to know SQL, so you're going to be writing queries that are going to gather this data. They want this. I don't know if this person wrote the ad. There's too much stuff going on here. 5 + 3 + 3 years + 3 years. You'd have to be like 100 years old to get this job. But anyway, so I'm not sure that this was written correctly. But they basically want you to have this collection of know how to use SQL. I'm surprised the other programming languages are not here. Oh yeah, so all right, here's PHP is a scripting language. Here's R. Anyone see Python? I can't believe there'd be a data science job that they don't want you to know Python. But, all right, so we got PHP and R. So what those are, very popular languages. Oh, here's Python. I should give as a homework assignment, find a job that needs data science skills and doesn't need Python. I bet you can't find one anywhere, so. All right, so, and what those are is languages that are, it's very popular to use those languages and run SQL statements, get the data to come back, and then do all your statistics, and then take whatever you figured out and write that back into tables. Now when someone goes shopping on your website and you throw an item in your cart, we just run out to the table and we grab the 3 items that they also buy and we display those for you. Try to make more sense. So, and it's everywhere. It's the biggest field now. Let me see if Amazon.com. Sometimes if you go to the bottom of Amazon.com, the page keeps building and building. Oh, good, it stayed. All right, so they have a careers thing, Amazon.com. And you do a search on data science. And again, tons and tons of, oh, they have, right now they have 370 job openings. If you can see that, 370 job openings, needing people who know data science. Oh, the head of data science, Newark, New Jersey. So supposedly Amazon's putting its headquarters in Newark, New Jersey. Did you hear that on the news? I mean, it's kind of still in discussions, but anyway, there's a lot of jobs nearby. So the head of data science would need to know all right, so this is the head job, but so they want a PhD or a master's degree in statistics. No computer science. Statistics, math, or physics. Knowledge of C, MATLAB. MATLAB is a tool that can do statistical data. Python, R. These are all statistical data, statistical programming languages. You mostly get your data from issuing SQL against a database. And based on your interpretation of what that data means, you do check results. And so yeah, so very popular among websites like Twitter, Facebook, and Amazon.com that do this big data analysis, read the data, and then as people are making moves on your website, you throw suggestions at them of things they might be interested in.